Namaskar my dear friends. Let us talk about Ethernet physical layer transceivers. So how we can design a schematic for Ethernet connections for around 10 Mbps or 100 Mbps or 1000 Mbps, or as it can go ahead as high as 40 GB per second as well these days. So as you have seen that lot of places Ethernet connections are used. As you can see, there are RJ45 connectors, right? So wherever there are servers or computers, laptops, or these days automotive industries, lot of them are using, and even industrial applications you will see there are a lot of automation techniques where you will be seeing these kind of connections, right? So these are the very high speed signals that will help you to send your datas at very high speed, right? So we have to understand what are the things that we should take care of while designing the circuit for Ethernet interface. Okay. At the same time, we'll try to understand one of the application using DP83826. Okay, this is the IC that will be utilized for giving you 10 Mbps and 100 Mbps industrial Ethernet as PHY applications. So let's talk about what is Ethernet and what are the terminologies that is available here. So as you can see, this is the particular IC that I will be taking care before giving you the explanation of Ethernet. Okay. So as you can see, this is a DP83826 deterministic low latency, low power, 10 to 100 Mbps industrial Ethernet PHY connection. Okay. According to IEEE 802.3, so what are the things that we will be seeing in this particular session is there are a lot of terminologies that are involved in Ethernet PHY connections. Like as you can see, this is a block diagram that you will be seeing. So this is the red block which is actually designed by Texas Instrument itself in one of the training session that I liked a lot. Now this is the particular thing that is your Ethernet IC, and now it will be getting interfaced with your Mac. Okay, that is Mac, and Mac will be nothing but your microprocessor or your FPGA, or let's say ASIC is there, or like a lot of processors are there. So those things will be utilized as a MAC address. Okay, and the outside it will be going to the network, and this network will be connected through RJ45 connector. As you can see, the RJ45 connectors look something like this. Okay, so these are the things that is there. Our understanding will be what are these RX-TX line and how it is controlled, what are the different control lines or signal lines that are utilized for circuit designs, and at the same time how we are going to put the isolation between RJ45 connectors and the networks. All these things we'll try to understand one by one. So this is going to be a very basic to advanced level understanding about Ethernet connection design. And let's talk about why we are talking about Ethernet PHY connections. So as you can see, wherever you go in your offices or anywhere in the world where it is, whether it is transports or whether it is movie theater or any places you go, you will be seeing a lot of Ethernet connections everywhere. And this is the reason it is very important, and we are entering into a situation where we need as high as like data rate as possible. So let me just list out the things that we will be talking about in this particular session. So we will talk about what are the different terminologies that is involved in Ethernet PHY connections, that is physical layer transceiver connections. Then we will see some of the schematic design techniques and applications, and at last you will understand a complete understanding of Ethernet schematic design. What are the requirements and how we should proceed. So why don't we go ahead with the data sheet of this particular IC that we have taken, and so that it will give us an idea about what are the things that we should take care while designing the circuit. So if you see the particular features of this particular IC, which is DP883826, okay, so this is the particular IC that I have taken. This is going to be very low and deterministic latency, where we can see the transmit latency is just 40 nanosecond and receive latency is just 170 nanoseconds. It is very robust and small system solution. It is integrated circuitry for EMC application, as well as you can see according to IEC 61000-4-2, which is the ESD standard, and for contact it is going to be plus minus 8 kilovolt, and as well as For air it is plus minus 15 kV, so you don't need to have external ESD diode protection circuitry. You can see EFT standard as well, that is IEC 61000-4-4. So that is EFT standard, which is going to be plus minus 4 kV. This is also applicable to CISPA-22 conducted emission class B. So CISPA-22 conducted emission class B and CISPA-22 radiated emission as well class B. Then it has fast link drop less than 10 microsecond. The cable reach can be as high as 150 meters. So generally these days people are using up to around 100 meters of cables. Okay, that is around 350 feet. So this is well applicable for that understanding. It has voltage mode line driver. It has integrated termination on MAC interface, and the voltage tolerance is up to plus minus 10%. Okay. Now there are two selectable pin modes in single device. So only one device is having both of them. One is basic mode, and at the same time one more is enhanced mode for additional features. If you talk about the power consumption, this is having very low power consumption, which is less than 160 milliwatts, and there are two kinds of MAC interfaces. One will be MII, that is your media independent interface, and one is RMII, that is reduced media independent interface. We'll talk about all other kind of MAC interfaces like GMII, RGMII, all those things are there, which is for high speed data rates. But in this particular session we will stick to only these two, which is going to be MII and RMII. If you talk about programmable energy saving modes, we have active sleep mode, deep power mode. So all these things are very well known features for any of the ICs that will be designed, so that is nothing to worry about. However, we can go ahead with the supply voltages. So supply voltage, as you can see, we are going to have 3.3 volt supply modes. And the IO voltage range, as you can see, we have 1.8 volt capability as well as 3.3 volt capabilities. So we will stick to 3.3 volt capabilities so that we can reduce our design complexity. It has RMII back to back repeater modes, and as you can see, the temperature operating range is minus 40 degree centigrade to 105 degree centigrade. Okay, so generally people go ahead with 0 to 70 degree centigrade or 0 to 85 degree centigrade, or like minus 40 degree centigrade to 85 degree centigrade, but it has little bit higher range, which is minus 40 to 105 degree centigrade. Okay, you can go ahead with as high as possible like 150 degree centigrade also for high temperature range applications. Now this is compliant with IEEE 802.3. so I will be talking about a lot of times for IEEE 802.3, and that is compliant for 10 base TE and 100 base TX. So 10 base means 10 Mbps, that by default you take it now itself, so that whenever I talk about 10 base, it means you have to understand 10 Mbps, and 100 base TX means 100 Mbps. So hope you have a very good understanding about the features that this particular IC is presenting to us. If you talk about the applications that it can be utilized for this particular IC, which is DP83826 that we have talked about right now, so you can utilize this particular IC in your factory automations, robotics or motion controls. We have motor drivers, we have grid infrastructures, we have building automations where you need to have lot of Wi-Fi connections or internet connection or server connections, all these things. We need to have industrial Ethernet field buses, so there also you can utilize. If you want to utilize for consumer applications also, this particular IC you can utilize. There is no need to have any problem. Like consumer electronics, you can utilize it in STB, OTTs or IPTVs, game consoles. People utilize a lot of things, like for gamings, so that you can use. You can utilize this thing in your printers, HMI and IP cameras as well. So as you have understood about the features and applications about this particular IC, now let us try to understand what is the typical application circuit that will look like. Okay, so let us say this is my IC, that is my Ethernet IC. So this Ethernet IC will be having two interfaces. One will be your MAC interface, that is left side. So this is my MAC device, which will be, let us say, my microprocessor or FPGA. So our design is actually on FPGA, which we will be giving you just in our next session, a complete design circuit with one of the FPGA that we have taken from Spartan, as well as one more FPGA we will be taking from Intel. Then you can utilize it for ASIC also, or SoCs also, as well as, you know, like a lot of different particular devices are there, that is like processors or something like that. So this will be called as MAC. Okay. The other part is the network, which will be going through the RJ45 connector. So this is going to the network where you are going to send the data. So this is how it works. The other part that works is, like, let us say this is my particular Ethernet IC. So this is going to have a reference clock of 25 megahertz, 50 megahertz, or 125 megahertz. Then it will be having like interrupt pins, and then it will be having MII or RMII, master slave interfaces. This is the one that we are going to talk about a lot for different applications. It has a station media interface as well, so that we'll talk about, like MDC and MDIOs. So what are these things? Like management data clock is there, and management data bus is there, so management data input output pins. So how we are going to manage this particular addresses so that a particular device can be recognized very clearly. Now if you talk about the right side, so right side we are going to have MDIs, that is called as media dependent interface. So media dependent interface is nothing but this is having a lot of, you know, like integrated MDI terminations, and those will be helping us to interface through the RJ45 connectors. In between, either you can utilize magnetics for isolation purpose, or without magnetics, if you want to go ahead for low end application where you don't need to go ahead with you know, like magnetics, then you can go ahead with decoupling capacitors as well. That also we will talk about. And you can see these days RJ45 connectors are actually coming up with magnetics included, so there also you can utilize. The most important thing is the power supplies that for IOs, that is either 3.3 volt logic level or 1.8 volt logic level, and the analog voltage supply, which will be 3.3 volt for this particular IC. And there is external clock as well for master application. You can utilize it either 25 kilohertz 25 megahertz crystal oscillator, or if you want to utilize reference clocks, then you can put it 25 megahertz or 50 megahertz. Similar to this particular IC, one more IC we had utilized in our low end application, which was 25. Right now we are going to talk about DP83 Now this was 83 So this has little bit lower end, which is reduced MII interface only. And as you can see, we have same thing like reference clock interface, and we have RMII interface only. What we are going to talk about is having MII as well, and this is having MDC and MDIO interface. And right side the same thing, magnetics with the network connections. Okay. So let us get into the IC pin configuration so that we can have an idea about what are the pins that is actually involved. So if you talk about this particular pin configuration of this particular Ethernet physical layer transceiver IC, so as you can see, we have like mode select pin, we have lot of other pins that we'll see you know, like one by one. So this RD minus RD plus is like receive pins, then TD plus TD minus is actually a transmit pin, and these two will be actually going to your RJ45 connector. Okay. Now let us talk about other pins. So we have crystal oscillator output, and there will be crystal oscillator input as well. That will be your XI pin, so which is XI pin here. And then we have here XO and XI is done. We have MDIO MDC pin, and there is bias pin that we also will talk about, like what is bias pin. And we have like RX pin. So RX data pins are there, 4 pins like RX D0, D1, D2, D3. Okay, so these are the things that is there. As you can, you know, like later on I'll make you understand that more number of data pins can be used for more data rate. Okay, so if you have to increase the data speed, then you can utilize more number of data lines. Otherwise, less number of data lines also are used to have lesser speed. Similar to that RX pin, we have TX pin. So like TX data pin 0, 1, 2, 3. So that is your transmit data rate signals going to the MAC pin. Okay. Rest others will try to understand through the pin description. So let's get into the pin description. So as I already mentioned, like RDM, RD pin, that is plus minus pin. Okay, this is called as differential receive input. Okay, so this is differential receive input coming from your RJ45 connector to the physical like Ethernet pin. Then we have a differential transmit output. So differential transmit output is actually going from your Ethernet switch to the RJ45 connector, that is your network connection. Okay, we have crystal output, that is XO and XI, that is crystal oscillator input. We have R bias, that is also called as bias resistor. Generally it will be connected 6.49 kilo ohm with 1% precision, okay, to the ground. So that is the understanding we have. We have MDIO, that is management data IO. So that is bidirectional management data signal that may be sourced by the management station or the PSI or PHY. Okay, and it has internal pull-up resistor also, which is of 10 kilo ohm, and external pull-up resistor can be added if it is required. That we will talk about during the circuit design. We have MDC, that is your management data clock. To next thing, we have the receive data signal. So receive data, you can see this will be getting connected to your MII modes or RMII modes as we need. Similar to that, we will be having VDDIO, that is your IO supply voltage. We have RxDV, that is nothing but receive data valid, okay, or CRSDV, okay, so that is data valid signal. We have RX clock and we have RX error pin, so that is receive error pin indicator. Okay, similar to that, we have power down connector or power down default is there, that is also called as interrupt pin. Then coming to the like text transmit pins, so we have transmit clock, we have transmit enable, and we have transmit data signals. Okay, then we have transmit error signal also, and we have at the same time, these are called as like LEDs. So there are LED 2, LED 3 and LED 0, so and LED 1. So there are LED 0, 1, 2, 3, 4 LEDs are there that can be utilized for your status indication, and one more last pin is there which is called reset pin. Okay, so in short, you have understood like what are the different pins that will be available for the Ethernet like circuit designs. So in short, in summary wise, if you see, we have like voltage supply pin, that is VDDA and VDDIO, that is your supply in IO supplies. Then we have RD minus RD plus, that is your receive data input, receive data output, and then transmit data input is there. Okay, so these two are for network connection. We have XI and XO, that is your crystal oscillator input output pins. We have R bias pin, we have management data IOs and management data clock pins. Then we have RX, that is receiver side, and we have transmitter side, that just now we have already explained you. Okay, so receive data valid, receive clock, receive error indication. Similar to that, we have transmit enable, transmit clock, and transmit error signals. Then we have LEDs and reset pins. So these are the like pins that will be available for my Ethernet PHY connections. Now let us talk about some of the terminologies that will be frequently using. So that is something called as MII. So you can have this particular list in your like notebook or in your pen and paper. Like MII, that is media independent interface. Then we have RMII, that is reduced media independent interface. Okay, so RMII is reduced media independent interface. Then we have GMII, that is called gigabit media independent interface. So GMII will be having higher data rate. Okay, and RMII and MII, I will tell you like what is the difference. Reduced MII means the less number of pins will be required for the interfacing. That's the only thing. There is something called as SMI, which actually serves as the MAC address indicator or something like that. So that is also called as a station management interface, and this is a two-wire data interface. We have these are the like 3-4 things that will be there inside the Ethernet PHY like a system or Ethernet PHY IC, that is called as MDI, that is media dependent interface. We have PCS layer, that is physical coding sublayer, and then we have PMA, that is physical medium attachment layer, and we have PMDs, that is physical medium dependent layer. Okay, now if you talk about different terminologies and different connections, so I have taken it from AMD. So as you can see, If you talk about Ethernet physical port details, so I am going to talk about MII. So that can give you a speed of 10 Mbps or 100 Mbps based on IEEE 802.3 speed. Okay, 802.3 standards. So as you can see, these are the signals that are actually involved in your MII port details. So in MII port details, we have 4 TXD lines, that is your like TMAC to PHY transmit data. Okay, and we have TX enable, TX like error signal. Similar to that, we have 4 RXD lines, that is your PHY to TMAC receive data. All right. Then we have RxDV, Rx error is there, and there Rx clock is there, and then TX clock is there. Similar to that, other port details are there. So if you talk about GMII, that is your gigabit media independent interface. So in that we have 8 data lines. So like 8 TXD lines are there, 0 to 7 you can see. We have TX enable and then TX error. At the same time, one more thing is there which is called as GTX clock. Okay, that is extra. Similar to that, if you talk about RxD lines, that is also 8 data lines are there. Then we have Rx data valid is there, and then we have Rx error, Rx clock, and TX clock. So Rx clock, TX clock is there. At the same time, one extra clock is there which is called as gigabit transmit clock. Okay. If you talk about reduced one, so reduced GMII is there, which is going to have 4 TXD lines and 4 RxD line. We have TX clock, a control line, and we have like transmit control line, and this is transmit clock line. Similar to that, we have Rx control line, and then that is your receive control line and receive clock line. But anyway, our scope of understanding will be right now RMII, which will be little bit less number of connections that we'll talk about when discussing the signals. Now let's get into the physical layer transceiver connections, like how it works and how it looks like. Okay, so as you can see, we have, let us say, a FPGA which is working as a MAC interface. Okay, and then from MAC to this PHY, we have the transmit lines or the receive lines, that is your data transmissions. Okay, and we have lot of clocks and status signal as well as control lines between MAC and PHY. We have a reference clock that will be used for the clocking purpose, and at the same time from here we are going to that this is also called as MII signal. Okay, that is media independent interface. Here only we are going to have different terminologies, like RMII will come up, and then GMII will come up. Okay, so like that, and then RGMII will come up. So there are a lot of media independent interface technologies based on the number of data lines that will be utilized, or number of like control signal that will be utilized. At the same time, what is the data rate that is going to be used. So based on that, different terminologies are coming up as MIIs. Okay, that is called as media independent interface. Okay, coming back to MDI, that is your media dependent interface. So that is going to be your transmit and receive signals which will be in differential pair lines. Okay, and that is going to have AC coupling or isolation. Here it is called as magnetics. Okay, so that will design, and this magnetic actually helps us to like have AC coupling as well as isolation, and then it is going to go to the RJ45 connector, and this is going to send the data to my network, which is like your server or PCs or wherever it is that is connected to your connector. So this is the complete understanding of your Ethernet system. And there are LEDs that will be indicating the status, like green LEDs or like yellow LEDs or red LEDs, whatever the things. And these LEDs are actually these days like connected in your connector directly. So these LEDs will be actually blinking here near the connector. So this PHY interface will be making sure to give the status based on the things that is happening inside the system. As you can see next, just now we had explained you like this is particular like Ethernet connection, complete Ethernet system. So Ethernet system is having PHY, which is physical layer transmission or physical transmission layer, transceivers layers. Now what we are going to talk about, it is having PCS layer, it has PMA layer, and it has PMD layer, and these three layers are actually making sure the data like encoding and decoding and all those things. So like basically PCS is going to encode the data into these lines, and then PMA is going to take care of that stack up or something like that, and PMD is going to take up the decoding and then sending it to your TX and RX data lines, right? Similar to that, we have this side, as I already mentioned you, this side we have MAC connection and this side we have network connection. So alright guys, hope you have a good idea about what is Ethernet and how it is going to be utilized. Okay, so now in the next session what we'll do is we'll try to explain this particular data sheet and try to understand the electrical characteristics, and at the same time some of the designs and details, what are the things that is applicable regarding this particular Ethernet PHY connections, and how we can develop the circuits very quickly. Okay, so hope you have a good understanding or good idea about the terminologies that are utilized in Ethernet PHY connections, and in next session we'll try to develop the circuits using DP83826. Thank you so much.